think I should switch this screen. Okay, so hopefully you can see my screen, full screen, and I did share the right screen, correct?
Yes.
Okay, great. Thank you so much. So today I'm going to talk about event-based fault diagnosis under different levels of uncertainty, and this is part of the effort under TC3, which myself and a couple of other colleagues that are working toward how we can detect faults and then react them. Reacting to those faults are being taken care in other TCs, but our TC is more or less toward the runtime fault detection and diagnosis, and also reachability analysis by other colleagues. My group focus is on fault diagnosis itself, and I'm going to be talking more details about it. A little bit about the background. I think it's good to start to say what is fault. Fault is we can have different definitions. I try to come up with a pretty simple definition for fault: malfunction in system components, actuators, sensors, or any other components that you may think that results in unacceptable system performance or system instability. So a couple of facts about faults. No matter how good engineering practices you deploy, how much you're gonna do the verification and testing and validation. Um, After you complete the design, we will come up with situations that, despite all these efforts, faults still may happen in the system, and it may happen anytime, anywhere in the system. F-35 is one of the most expensive platforms, and best engineering practices have been used on that. And you can see even that one ended up with some failures. And then one thing at the time of failures is failure occurrences is important is to conduct a diagnosis, and that diagnosis can be done manually. Start looking at manuals and then see, okay, now how we can do troubleshooting and then identify the source of failure. But that's not really a good way, especially for safety critical systems such as aircrafts. And then alternative to this would be deploying sort of automatic fault diagnosis. Why is it important? The time when a fault happens, especially in fault critical systems, is important to quickly detect this fault and identify the type of faults to come up with sort of resolutions. There have been multiple accidents, including the flight 191, 1971, and that's 15 seconds reaction time was possible to recover the aircraft, but that didn't happen, and unfortunately ended up with a crash, and and that highlights the fact that it is important to quickly identify the faults in a correct way. So, and the time is matter here. So to detect faults is is another example is the launch of Antares rocket, and after 15 seconds of the launch, it was exploded and damaged the launching pad. And gladly there wasn't any fatality, but still a lot of investment and development efforts was damaged by these accidents. So. I'm not going to go through the details of the accident investigation report, but I wanted to highlight a couple of facts that the according to that investigation, the sensors and that might be and the instrumentation suite for engines during the flight was not sufficient to gain adequate information to react to the faults, and there was some recommendations. The recommendation was to use better sensors and more sensors, and the question here is that are we able to place sensors for detecting faults and then sensors on the top of sensors? That's not really practically useful. Certainly, we wanted to avoid single point of failures, but yet how much that is enough, and then sensors on the top of sensors, that may not be a practical sort of situation. That leaves us with the challenge to detect faults under partial observation. And I'm referring to the term diagnosis quite often. And by diagnosing faults, I refer to three basically problems: detecting faults, identifying faults, and locating the faults. Whether the fault has been happened, what is the type of failure, and where in the system that has happened. And to summarize so far what I said, faults may happen anytime, anywhere in the systems. Practically, we cannot have dedicated sensors for every single possible failures that can happen. And not always we have access to the model of the system, and we have a lot of uncertainty or unknown information about the systems. And yet, despite all these challenges, we have to detect fault as soon as possible. Uh, there have there are different approaches to detect faults. What but and what the research method that we are using in our group is using discrete event systems, and I'm going to be discussing about this method in more detail shortly. But the rationality of using discrete event systems is that they're pretty following a logical model that we as human also using cause and effect relation, and then it's a more abstract model that we can use to and that's pretty manageable information exchange of a sequence of events that are happening in the system and the relation that we can establish in that way. So more specific about the discrete event systems, the core is automaton. Consider a vending machine. And sorry if this information, part of it might be too kind of basics, but I think it's, and I'm not going to discuss too much details on the basics and backgrounds, but I think it's important to know the notations. And I'm trying to use a very simple model of the vending machine, how it's being operated. So you can have different states. You insert the coin, you select the items, and you receive it, and so on. And each of the transitions and events that are happening, you insert a coin. There is not enough coins, or you select an items. The red ones are sort of events, the labels that you can see on these transitions. So that can be abstracted with set of states shown by either circle or square, and then the labels on the transitions that are events. And these events can be observable or unobservable. So now with this symbolic model referred to as automaton is a couple of components, states X, 1, 2, 3, 4, 5. These are the states, and the events, the labels on these transitions, which can be observable, sigma O or sigma U unobservable events that we may have. And then the transitions, when you are in a state and an event happen, you may transition to the other states, and the initial conditions, x0, which is 1 here. We do have strings that a sequence of events that may happen in the systems, and the language, the set of all the strings that may happen in the system. We define projection um, uh, over the strings, basically, especially the projection to the observable event set. And why is it important? Because we have to detect faults based on observable behavior of the system, and that observable behavior of the system can be best captured by natural projection. And that natural projection is eliminating the unobservable events in the string, and that leaves us with the observable events in that particular string. And then we can extend this natural projection definition to the language, and also define the inverse of natural projection, p inverse of the language. So I made it short so that we can go to the actual proposed framework that we have been using. So now, having the system that is modeled by discrete event systems, we can observe the behavior of the system using natural projection, and the objective is to diagnose faults, detecting faults, and then isolating and identifying the type of faults. This block that is detecting fault, isolating, and identifying is called diagnoser. And the objective here is to detect faults based on observable behavior of the system. So this has been field. I mean, the very first paper perhaps have been shown up in the that I was able to find was 1995, and since then there have been so many results showing up in the literature. But one thing that is have been always challenging is how to handle all these problems when we have uncertainties in the system, when we don't know the systems is unknown, or we have uncertainty in terms of different aspects of the system, especially the initial condition of the system. And we have been focusing on addressing these challenges, and we have been using several methods to address the uncertainty and partial or unknown models of the system in terms of discrete event model of the system. And different methods, active learning methods, which I'm going to be talking more about it today, asynchronous diagnosis and semi-asynchronous diagnosis when we have uncertain initial conditions. And that's something that still we are working on it. But today's focus primarily, I'm talking about active learning. So a couple of assumptions that we are making about the system under diagnosis. First of all, faults are unobservable. So that's not really a restricting assumptions, because if the faults are observable, they are trivial to be detected. So we make it more challenging for us and say that, hey, now assume that the faults are unobservable, and then try to diagnose faults under that assumption. So that is not a restricting assumption. The other thing here is that um, we assume that the faults creating an abrupt change in the system, and they can be captured as an event. So that's not all faults have this sort of feature that you can see abrupt changes or creating some sequence of events in the system. And then the other thing is that we assume that the fault does not bring the system to a halt mode so that the system continue operation, and we have enough time to observe the behavior of the system and diagnose the fault based on the observation of the system behavior. We don't expect that the system to be fully observable. Under partial observation, still we need to be able to observe the behavior of the system and detect the events that are happening in the system. And as I mentioned, we're going to be using active learning techniques. And just a little bit background, in passive learning approaches, you provide all set of information to the system. You train the model of the model that can infer the force based on the training that is provided, with some level of generalizability, but that's always limited, especially when you are when your trained model is facing a completely new sort of scenarios or situation. In contrast, when we are talking active learning approach, the system or the diagnoser or the learner is more actively engaged in that learning process, and it comes to the trainer or teacher or oracle and ask about the information that are missing, and then try to fill the gaps if there is any. So the uh, the method that we're going to be discussing today here is the system under diagnosis is unknown. We're going to be using an active learning technique to diagnose faults in the system. The way that is working is the active learner is asking basic minimum questions or queries to an oracle, and we assume that oracle can provide correct answers to the queries. And we also develop an independent label propagation to track the information that we have collected so far to minimize the queries to the oracle. So what is what does it look like? Here is on the bottom left, you can see the discrete event systems of a plant is a synthetic model that we have several models, and the faults F1 and F2, for example, that we have here. And what we're going to be using, generating a diagnoser, and this diagnoser on the right side will be constructed using an active learning mechanism. So we don't have it, we have to build it, but I just show the end product. How does it look like? And as you can see, this diagnoser on each state does have several labels, and these labels could be either normal or faulty. We might have different faults, not a single faults, different types of faults, let's say M faults that we may have. And then we might not always be clear whether it is normal or faulty. We might have ambiguity in terms of whether fault type Fi has happened or not. So that's why you can see N or A1, A2 referring to ambiguity in fault F1 or fault F2, and then gradually the system can diagnose the fault and leads to the states that are really you are determined that the fault F1 has happened. So the mechanism for the active learning procedure that we are developing is the algorithm gradually learn and initializes the system and try to collect the information through a process, the basic minimum queries, and a label propagation mechanism is being used to keep track of the past information and also the after completing a set of observation tables, we put them together to complete the knowledge base that we need to build the diagnoser. The queries that we are making to the Oracle or trainer are our two basic queries is membership queries. We have observe and a string, and we can ask, hey, whether this string is faulty or not, and then equivalence query. Once we construct the diagnoser, we are coming back and saying that are we missing any kind of strings in the system or not. The whole process is captured here. We initialize the observation tables. We go through several steps. First, check the closeness of the observation table to make sure that all sequences are possible sequences have been captured, and also making sure that all information are consistent. When the system is close and consistent, we refer that our observation table is complete, and then we can hypothesize the diagnoser. And then once we hypothesize the diagnoser, the counterexample query is met. Hey, are we missing any example? And the if yes, a counterexample is returned, and we have to go through this process again. And then when there is no counterexample, the correct diagnoser is returned. So to explain the process, imagine that we have a system with some with some events. So this is the observation table on the right corner that you can see. The set S, capital S, is the set of events that we do have, and then their concatenation on the second part of the observation table. And then the elements here, N0, A1, and whatever. So these are the elements that we have to apply the condition map to fill this table. So they are not initially given, so we are applying this condition map to complete this observation table. And how this condition map is working is for a given string, if that string doesn't exist, the elements in the table is 0. If the string is normal, no fault is happened, so the label is N. Otherwise, the label would be either Fi, which stands for fault type Fi, or AI, ambiguity in fault Fi. So, and this condition map, we have to make sure that is determining what type of queries we have to make to the Oracle. And to minimize these sorts of queries, we use a label propagation mechanism, and that's pretty simple and rational. If a string is faulty, then of course all subsequent strings and all its extensions are faulty too. And if a string doesn't exist, certainly all concatenate all extensions of that strings also does not exist in the system as well. So these two simple rules here are significantly reduce the number of queries to the oracle. So as I mentioned, we start with initialization. Initialization is we start from epsilon, meaning that empty strings. So S initially is epsilon, is empty string. So initially the system is normal, and we make queries to the system and to the oracle, and it's saying that, hey, what is the status of A and B? And the oracle would say that there is no string A can be generated initially, so it is 0, or initially the system is under ambiguity. So these two queries are initially met to the oracle. And this is just one sort of examples that you can see. I will have more detailed information about the systems under diagnosis when we are making these queries. And then we check for closeness. What does mean closeness? All all elements that you can see here, 0 or A1, they should exist on the first part of the table S. For example, here, 0 and A1 does not exist here corresponding to the first part of the table S. We only, under S, we have only N. We don't have any 0 or A1. So we have to make what, if the table is not closed, what do? We make it close. How? We add these two rows to the first part, and all concatenation of these events are being added to the second part. Sorry, I got a little bit cold, but hopefully I can continue the rest of it. And sorry if I'm coughing for now. So we have this. If the table is not closed, we're going to be adding these rows to the first part of the table. And then all concatenations also have to be added on the second part of the table. So in that way, we are making the queries. And we can fill this information in the table based on the existing information, or we have to make new queries to the oracle. Typically in these tables that I'm showing, if there is a new queries to the oracle, I show it with red throughout this conversation. So these are the new queries that are making to the oracle. The rest of elements of the table are completed based on the existing information that we have here. Another check that we have to make is the consistency. The consistency is that if we have two rows that are the same, for example, here A1 and A2 are the same rows here, their concatenation with some other events, for example, now we have B, its label is A1, and BB, its label is A1 too. Their concatenation, what are their concatenation with other events? For example, BBA and BA. So their concatenation also with other events also should result with the same label, but it does not here in this case. You can see one of them concatenation with A is leading to label N, another one is leading to label 0. What is happening here is the table is inconsistent and we have to make it consistent. How? The event that has created this problem is A. We add the column A here, and then we have to complete the new observation table and complete it. And then of course some of this information can be completed based on the existing information, and some we have to make queries to the oracle that are highlighted in red. Once we make the system close and consistent, then we can now hypothesize a diagnoser. The diagnoser is from this table. We can construct this automaton. Each row in S part, excluding the 0, 1, is a state in the diagnoser. The transitions are also captured in the elements of the diagnoser. For example, if you are in state N, so concatenation with B, you go to A1. You see N goes to A1 with event B. And again, if you have another B, you go BB, so you go to A1. So that's a self loop here. So from this table, we can construct this diagnoser, and that is the hypothesized diagnoser that we do have. Making a queries to the Oracle again. Hey, is it something missing? Is there a counterexample that is either the Oracle answers, or we observe adaptively throughout the system, and we identify throughout the observation of the system. So adaptively, we can incorporate this information. Now, once we detect a counterexample, let's say BBA, this counterexample has to be included in the table, and all, so BBA is now added to S, and all its prefixes are added and to the table as well. And then we have to go again through the closeness and consistency process. So for this automaton that I initially showed you, we have gone through all these steps to detect the final table, which is T7. And this T7 is resulting the diagnoser on bottom left side of this slide. The queries that we have met is not a lot. All are in red. So those that have been met, so these red elements are those queries that we have met to the Oracle. The rest of it is constructed based on the available information of the table and the label propagation mechanism. And in each of these steps from one table to another table, we have been checking if the table is close, is consistent, and then we hypothesize the diagnoser, we checked for the counterexample and have gone through this process until we end up with a table that is close and consistent. So to understand now what this final product is working is the system diagnosis on the left and diagnoser is on the right side. The unobservable events, I think here is only false. That doesn't have to be only false, so we might still have some events that are unobservable and they are not faulty. But here is a very simple, basic system that we do have. So the diagnoser and the system are under diagnosis. They are running synchronized, meaning that if an event happening here, B, that is observable, that causes a transition on the diagnoser as well. For example, you see that the event B happens here. The system under diagnoser transition to 2. Correspondingly, there is a transition in the system under diagnosis. We continue, the system under diagnosis goes to state 3 by observing event B, and then the diagnoser also transits. So the diagnoser is running concurrently with the system under diagnosis. And then we can also see the labels. For example, now the system transit to state 1. The diagnoser also transit to 1N, and the label is N, meaning that so far the system is normal. So then the system under diagnosis transits to 2, and then A1, and then there is an unobservable event that is happening. So the system under diagnosis, the diagnoser cannot observe the unobservable event, so there is no transition on the diagnoser part. And then until you finally end up with a fault happens, and you transit to a system, to a state that is faulty, and you can say fault F1 has happened. So we have proven that this active learning process is resulting in minimum diagnoser in terms of the number of states. It creates a deterministic diagnoser, so it is important to be deterministic because non-determinism on the decision making under the diagnosis part is quite strange. You want to have as deterministic diagnoser to make a more accurate decision. So the diagnoser that we are creating here is deterministic. And this whole process, including multiple loops for checking consistency, closeness, and counterexample, is proven that is being terminated and eventually will lead to the diagnoser. So more details about this process just recently published, and you can see if, and I can share this paper with you if interested to read more details about this method. So Now, with these the tools that we have developed, some other research questions that right now we are working is when the system is partially known. So what I propose here was when, what's applicable to the case that the system is completely unknown. You are trying to use a sort of active learning mechanism to diagnose the to build the to understand the system and at the same time diagnose it. What about the case that the system is partially known? If the system is partially known, the orange circle here is representing, for example, the partially known part of the system and the whole and out of the complete information that we have here. So one strategy is to ignore the known information and still apply what we discussed today. Um, uh, Trash all information that we know, and some of them are important, and we are not going to be using them, and you can apply the method that we just discussed today and try to learn the system from scratch. So that's one way. Of course, this is not a wise way of doing that, but the other alternative way that we are now working on it is to take advantage of the information that we do have and then try to actively learn the unknown part of the system. There are so much challenges how to handle this information and incorporate this the known part into the active learning mechanism and the initialization of the active learning mechanism. But I think we are having a good sort of results to be ready pretty soon. So we are almost there to address this problem. The other sort of problem that right now we are working is uncertainty in the initial condition of the system. As I mentioned, this sort of approach for fault diagnosis have been we have very initial results, let's say 1995, that we had it by Professor Lafortune. They have been working on this framework of fault diagnosis of discrete event systems. And as you see in the examples that I just shared with you, um, there is an assumption that the system under diagnosis and the diagnoser are working concurrently and they are completely synchronized from initial condition. That imposes a lot of constraints and not always this is doable. Recently, we have had some interesting results in terms of what if we don't know the initial conditions of the system, we don't know where the system is, either the initial the synchronization has been interrupted. We have some misobservations, or from the or the system has ended up with faults, and we bring our diagnosis tools and we don't want to restart the system to synchronize them. How we handle this sort of situation, we refer to this problem as asynchronous diagnosis, in which we don't know where the system is at all, and still we have to diagnose the fault. And just give a little bit insight, what we do here is that we take some time to observe the system, and then from that observation try to narrow down where the system is and then start diagnosing. And that time that we try to understand where the system is is quite critical, and that increases the diagnosis time. Another problem that right now we are working on it is the semi-asynchronous diagnosis, and that is under situation that it's not the case that we don't know anything about the system. We partially know where the system is. We just have a sort of belief states about the initial state of the system or the current state of the system, and then we wanted to know where the system is and then start the diagnosing of the system. Another research work that my student and Asmol and I are working on it is the applying all these techniques to the aircraft systems, and we are taking two approaches. Also we try to incorporate all these into the ground simulator, especially when we are talking about the system level diagnosis. But for now, what we are working is the component level fault diagnosis on the actuator, aileron, rudder, or so when as a sort of electro-hydraulic systems, and so many actual elements are engaged, and then when sort of faults happen in one of the components, how we can diagnose the faults. So that's the first steps that we are working, and then bringing all this into the system level diagnosis when we have a coordinated flight, and then in one of the actuators there's a failure happening, and then how we can diagnose the faults. And that's pretty much about the work. I would like to thank the team members, and Andrew White, when which was my former students, and unfortunately he was actually my first PhD students, and during the COVID time, unfortunately, he passed away. So we do have also Wendell Base. I think he's now with Lockheed. So he graduated 1 year ago. And Asmol and Jose right now working with me on this fault diagnosis. Also, thanks to the team members in TC3 and NASA ULI program. If there is any questions, I would be happy to answer now.
Ali, thanks a lot for this impressive presentation. Very saddening to learn about losing a student during COVID. This is kind of unfortunate, but we can't change much here.
Yep.
So yeah, Ali, so I mean, it impacted me. So regarding testing some of these algorithms on that Guam, so were you able to test it, right? You got the model, I'm sure, because we shared it with everyone. And have you tried anything with the model at this point or not yet?
So we are now still learning how to work on the Guam simulator, and then I don't think that at this stage, when we are talking about the component level sort of diagnosis, that would be very much helpful. We hope that we can incorporate and add some of these actuator models to the rest of the simulation, and then see when it comes to the coordinated flight, then we hope that we can see the integration into the Guam simulator. We are working on it. We just at this stage, to be honest, we are learning on it. So Asmol is very much focusing on this one, and we have had some supports and received I think 2 weeks ago the GitHub that was really helpful for that demonstrations and developments that they had that we have had, I think. So yep, but we haven't in the plan. We haven't been getting to the point to really incorporate anything yet, but we do have it in our plan.
Yeah, because if you have any questions on the model, we have had a few NASA sessions with the NASA team members who kind of guided us how to quickly get used to it, how to kind of debug what otherwise was maybe hard for us to understand and navigate. So in case if you need any help or guidance, we have already members in our team who can help you, or I'm sure NASA team would be also happy to get on a call with you. This is a resource you should use to accelerate these transitions.
Great. Yep.
And also the next question would be with this level of fault diagnosis with learning elements, right? So we want also Chris Elliott to come and guide how we can improve the TRL levels and have a maybe call with you, Chris. So and how to do integration with other team members' efforts and different methods coming out of this ULI. We're still in year one, kind of maybe it's too early to create the pressure, although I don't think it's too early, but it's the right time maybe already to allocate some of your resources and some of your budget for ensuring smooth integration with other team members and
Yep.
the models coming from NASA, right? So that's my only kind of comment at this point. And let's see if others have questions because the talk was very interesting.
So yep, I think that's interesting question, and just a little bit providing background. How are we handling this this in our TC and then with others? So I think there are three components that we have in our TC. One is discrete high-level fault diagnosis, which I am working, and then Yanis is working on the continuous the sort of fault continuous time domain fault diagnosis. So these two are complementary approaches. And then we feed this information to Melkor, who is working on reachability analysis. And saying that now under this fault happening, what is the reachable sets that we're going to be reaching. And I think from there is going to be incorporated into TC1, which is the fault recovery and sort of other aspects that we are doing. So I think that's the natural sequences that we go through. The next immediate steps is to feed this information to the work that Melchior team is working on it to now that under this fault fault detection, what is the reachable sets and so on.
Okay. Okay, good. So let's see if others have questions because we have lots of people here present. So no questions from others? Nobody wants to ask? Yes, Chris, go ahead.
Yes, I have a few questions. So first off, I'll just say thanks for the talk. Dr. Karimoddini, make sure I get your name right. That's a really inspiring work. I'm very interested in your actuator example. I think that could be a good example for us to leverage in the Guam model. Can you speak a bit to some of the faults that the diagnoser's trying to detect? Are they actuator runaways or actuator locks? I mean, there's a bunch of different types of faults that we could simulate with that actuator model, where maybe it's a mechanical break and it's just floating in the free stream, and maybe I don't have observability on that aspect of it if I don't have position feedback on an actuator. Or even degraded performance. Maybe I have a power failure on the system and I have a poor transient response on the actuator, or just a sluggish bandwidth. Can you speak a bit about where we could take this example with some of our applications?
Oh, yeah. So I think right now with this component level fault, we are injecting the several faults both on the mechanical components, on the piston, or let's say on the mechanical components of the system, as well as the electronic part of it. If on the electronic side of it there is a kind of challenge and problem. So right now we are injecting and detecting, developing a model for each of the actuators, both on the mechanical and electronic side of it. So the type of faults that my group is working again is the, for example, complete the kind of disconnect on the mechanical, let's say on the piston is completely stuck or whatever, right? So it's not degraded performance, but I think we can incorporate a degraded performance, but that's the work that my other colleague, Dr. Raptis, is working on that, and not this method might be applicable when we do have degraded performance on abnormality in that sense. For us is kind of we should have sort of events that are happening, and that should be a little bit more than just degraded performance. And then yes, it is both on the mechanical and electronic side of it. We are trying to inject some sort of faults on both levels. We have had some initial force on the component level. We haven't got to the system level coordinated flight sort of fault injections. Soon I think we should have some results on the component levels and different type of faults and model of the system that we are using for the fault diagnosis.
So real quick, just a further question. So as you explained, the diagnoser interrogating or querying the system and learning that fault tree, finding the counterexample, and then potentially re-hypothesizing. I think you used the word hypothesizing the diagnoser. What's the level of computational time required, maybe as a number of states in that fault tree? How long does it take to produce that counterexample and then re-hypothesize in your example there? Are we talking milliseconds, seconds, minutes? I'm trying to relate this to a real-time operation in terms of number of states.
So I think it depends on the size of the model that we do have. If I'm not forgotten, the computation time was polynomial in terms of the number of states that we do have. I do have the computation time complexity for that for this approach, but the more challenge is the queries. that is I don't think that the computation side of the tables that we are making, the table hypothesizing the diagnosis and so on, that would be the major challenge. The major challenge is having the queries answered, and then either from data or from the expert that is able to answer that diagnosis, that queries. That is the bottleneck over there. But I don't think that the computation time of the observation, building the observation table and hypothesizing the diagnosis would be the major challenge.
Very good. Thank you very much.
Thank you.
And just a kind of a general question in terms of the reachability research. Have we looked at links to some of the other competencies, such as Dr. Mitra's VERSE tool that we heard about a few weeks ago?
I leave it to the, let me see if Melkor is here today. If not, I will check with him and or even Shine.
It's about Sayan Mitra's toolbox, that
Yes.
verse that he presented.
I think yes. I think Melkor and Shine are working closely on this one. Yes, we are working.
Yes.
Yes, we are working. They are working closely with each other, as far as I know.
Yes. So, Azmul, did you have question? I saw you hand raising a bit ago. Then you dropped.
No, ma'am. I was having a network issue, so I just wanted to ask permission to leave and rejoin.
Oh, okay. So more questions? Somebody speaking up or?
I have more questions. I'm trying to
Okay,
let.
go ahead,
Yeah.
please.
Yeah.
Okay, sure.
Yeah,
It's our time.
It's fascinating work. So when you're building the events, is the independent variable always time? You mentioned time histories. Could there be a different independent variable, for instance, like maybe a spatial independent variable where the failure or the event, the transition always occurs at a particular location on a trajectory? As your team considered that?
I think the term diagnosis that we were referring does have the ability to localize where the fault is occurring in the system, and the type of faults. It's not just to detect the occurrence of faults. We go more than that and try to say what is the type of fault and where is the location of the fault. So that's the beauty of the method, I think. And then the term event here is we have two mechanisms. One is event driven, which is different from time-driven sort of approach that, again, Dr. Raptis and his team are working on it. So events could be passing a threshold, or could be really something that is just a disconnect in or piston stock, for example, or no, the pressure in the hydraulic systems is exceeding a certain level. So either way could be considered as an event, but they don't have to be time driven. That's another sort of information that I thought might be helpful. Yep.
And then my final question, and I'll get off the stage, is you're showing a nice Simulink diagram here. Is there an example that you could share with the team with a Simulink implementation? Is this an implementation of the tool querying this model?
Yes,
Okay.
we are. I don't have it right now, showing to you, but yes, this is part of there was a existing toolbox for the Aileron architecture, I believe, and then we have been modifying it and using it, so it does have both visualization and all those components. So we are adopting and expanding our tools, that toolbox, and then hopefully we're gonna integrate it into the. If it's not available already, I think that's integrating into other components for the system level diagnosis. But yes, there is a Simulink model that we are using Asmol is already there. So Asmol, can you please put the link to this simulator if he's here?
Yes, Professor, I can send the link in the group chat.
Yes.
Okay, it's in the Teams chat, right?
Yes. So what you see the link is not what we have been expanding that toolbox, but I think that's the basic Simulink model that Asmol is putting in the chat box.
Great work. Thank you very much.
Thank you.
Did you get it, Chris? Chris, did you get the link?
Not yet. I'm still looking at the meeting chat. It just says recording has started. I don't see a link
Right,
yet.
the link didn't come. So
Okay.
maybe you said, oh, okay,
Maybe.
here it came, right. It
Yeah,
just
it's a bit
landed
slow
in
here.
there. Right, it's a bit slow. Okay. More questions?
Yes, I have a question.
Okay, go ahead, Yunji.
At the beginning of the presentation, I think you mentioned about active learning, but I missed some part of it because of network issues. Can you give me some summary of that problem formulation that use this active learning?
Okay. So let me see if I put it to exit the. So the the formulation is not just a brief story. It's not the problem formulation. The problem formulation, I can share you the paper that we do have, and that's provide the exact problem formulation. But we have a discrete event system G that we don't know that system. All we know is the observable event set. And then from the observation of the observable behavior of the system, which is captured by natural projection, we try to identify the diagnoser, build and identify the diagnoser at the same time. So that's sort of problem statement if it is not problem formulation. So G is not known. All we know is sigma O. And yes, from there and observing the behavior of the systems, which is strings, observable strings with observable events, we try to build the diagnoser.
Thank you very much. So in very high level, maybe it's not correct, but it is somehow related to optimizer kind of the meta learning kind of philosophy or approach.
Not sure, but I think what we have proven at the end that the automaton that we will be building as diagnoser is proven to be the minimum diagnoser in the sense that minimum number of states it will have. So that's in terms of optimality.
I think that when we prepared the proposal, you already have publication related to this active learning idea, right? Maybe I just need to take a look into it. Okay,
yes,
thank you.
I think that's the publication is listed here.
Okay, thank you very much.
You're welcome. Thank you.
Thank you, everyone. Do we have more questions? Maybe one last minute quick question. If no more question, we can close the team and put the recording and the slides, Ali. If you would not mind sharing the slides, we'll put it on the website.
Sure, I will do. Sure.
Thank you, everyone. And we'll post everything on the website and share the link and see you all next month, okay? And next month, Basu will present developments within the fourth trust. Thank you. Bye-bye.
Thank you. Bye-bye. Thank you, everybody.